Welcome back to your engineering mechanics class of your dreams. Today we're going to continue exactly where we left off last class, and specifically what we're going to do is we will take a look at internal force diagrams. This is the first time we actually introduce force diagrams. Those will be discussed throughout many of the following lectures. So today we're going to start easy and begin with concentrated forces. And to talk about that, first I want to generally introduce the general concept to you. So the graphing methods, how do we do it to display the internal forces? And once we have a general understanding of that and we have seen it actually in application, we can then learn how in future problems we will actually discretize rigid bodies. And discretizing just means that we're going to split it up into individual sections so that we can define individual domains so that we can properly graph everything that we need to show in these diagrams. But this will become more clear as we go throughout the lecture. And then ultimately our goal is to really represent the internal forces by drawing them. And again, today we only will do that for concentrated forces. And in following lectures, we will take this up a notch and talk about distributed forces and non-evenly distributed forces and so on and so forth. But now let's get started and generally think about the concept of graphing internal forces and bending moments. So what I want to introduce to you is how do we graph these force values and bending moment values that we actually calculated in our last lectures. So I want to start with this problem here. This problem has been seen in lecture 10, where we calculated the support reactions for A and B, and I will introduce those in a second just to remember those properly. And in lecture 13, the previous one, we actually calculated the internal forces at this location, and at this location to the left and to the right of the force. And our goal today is to actually properly graph those. So let's go ahead and first pull in the values from our previous lecture 10, where we calculated the support reactions. And one of the first ones was RAY, which we determined to be 11.43 newtons. And we also calculated the value, of course, for the horizontal support reaction, which we determined to push to the right with 43.3 Newton. And last but not least, we have support reaction B, which was determined with 23.57. And that was, of course, also in Newton. Let's remember real quick that we got the support reactions from lecture 10. So if you're really puzzled about the support reactions, please go back to lecture 10 to understand properly how you determine them, because as you already saw in the last lecture, we always need the external forces first to find the internal forces. And let's therefore talk about the internal forces that we actually calculated at this location here to the left of the force, to the right of the force, to the left and to the right of this force. And to do that, let me first bring in the dimensions. And let's remember that the beam had dimensions of, I believe, 4 meters on the left side. And then we had 1 meter in between the two forces. And we had 2 meters at the end here. And so those are the dimensions for which we calculated the support reactions really at this location, this location, this location, and this location. And we called that location at that time 4 meters to the left, for example, for this one, and 4 meters to the right. And then we called this here 5 meters to the left and 5 meters to the right. Why did we do that? Because we started our x from 0. So think of x moving positive in that direction. And because it's now our goal to actually graph these internal values and the values that we calculated in our last lecture, please go ahead and pull out your notes from lecture 13 and understand that the internal forces at the specific locations were determined in lecture 13. And so I have these values in front of me right now. You should do the same and pull up the notes, because we will refer to lecture 13, and that's how you will do it in the future as well. And please remember that what we calculated were the values for N, V, and M. So normal force, shear force, and the moment. And we did that at the specific locations of 4 meters to the left, at 4 meters to the right, at 5 meters to the left, and at 5 meters to the right. So we will use those values that we determined at these 4 locations to start our graphing efforts, and then I will show you how to extrapolate our knowledge that we gained from these 4 points to actually graph it for everywhere along the entire axis of the beam. And because we calculated 3 different force types here, or 2 forces and a bending moment, we now graph them on 3 different graphs that you can see prepared here for you. So we have 1 graph, 2 graphs, 3 graphs, and traditionally we usually put the normal force on the top and then the shear force and the bending moment. You could also put the shear force and then the bending moment and the normal force on the bottom. It doesn't really matter. What's important, and you will learn this today, is that there's always a relationship between the shear force and the bending moment. So to better see that relationship and to better utilize that relationship between the shear force and the bending moment, we always would put the shear force on top of the bending moment. So we could put the shear force here, the bending moment here, and then the normal force here. But again, traditionally, it's most common to put the normal force on the top. And because we want to use these values that we calculated here, 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 and here, I'm now first gonna bring down all my specific locations just so that I can better deal with them when I draw this. I don't always do this later, but for today, because it's the first time that we're doing this, please let's go ahead and faintly bring down these lines where something happens, as I usually say it. So I bring down all these lines, and in fact I even bring down the lines from the support reactions that will help me with better graphing. Okay, and now we need to identify which graph is which. And the first important thing, therefore, is to always identify what type of graph and what unit we have here. So let me go ahead and take it one by one. I'm going to start with the normal force graph, and I'm going to indicate this with a normal force, and I'm going to state that it is in Newton in this case. So let's be clear here, because this could be confusing right now because we have NN, but this stands for normal force in the circle, and then in the square bracket is the unit. All right, and now let's zoom in on that particular graph, and let's actually understand what we're trying to graph here. So remember that we talked about the dashed fiber here on the bottom, which indicates that this is a rigid body and which indicates that this is technically the bottom of the beam. So what that really indicates to me is that there's a positive x and a positive y direction. And in these graphs, you will never see this later, but because it's the first time we're doing this, I want to introduce this to you. So I know that x is usually going in this direction, and x is in the unit of meters, because I want to graph the specific values everywhere along x. And the entire beam here is 4 + 1 + 2 meters long. And so this point here would be x equal to 7, this would be x equal to 4, x equal to 5, and so on and so forth. And The other thing that this reference fiber tells me is that there is a positive and a negative side. And I mentioned this to you before, and you got away without really making use of this. But from now on, you need to memorize that the reference fiber is always on the negative side of the graph, and the non-referenced fiber portion is in the positive direction. So the way I will indicate this to you, purely for educational purposes, because nobody does this in real life, but the way I will indicate this is by showing you that here we have a positive y value usually, and here we have a negative y value. But keep in mind that this is actually the normal force, and so this is in newtons, in the unit of newtons. Again, you will never see this later on, but for your education this might be helpful. So what I'm trying to tell you is we have an XY graph which mathematically looks normal, and you may wonder, why do I emphasize this so much? I'm emphasizing this because the reason this is a normal mathematical graph with X and Y is because we have the reference fiber on the bottom. If the reference fiber was on the top, we would actually look at a Y-axis pointing positive downwards and an X-axis pointing positive to the left. But for our first example, for an educational introduction to these diagrams, that's obviously not something we need to worry about. We're just going to stick with the regular XY coordinate system. And our goal now is to actually graph the values that we determined. And remember that we determined the value here at 4.99999 meters. No, sorry, 3.999 meters, at 4.00001, and then at 4.99999, and at 5.00001. And so, of course, later on we're just going to call it left, right, 4 to the left, 4 to the right. But so that you clearly understand what we're talking about, let's now graph these values. And the way I prefer to do this is I'm going to go on my vertical lines now, and remember that the value that I calculated at this location to the left of this vertical line was given with, if I'm not mistaken, negative, and the negative is very important obviously now, 43.3 Newton. And the next value that we determined is on the opposite end of that line. So that, of course, was also negative 43.3. And then we had another value that also turned out to be negative 43.3. And we had a value of 0. So now we know those values, and the question is, how do we graph them now? So I guess it's actually not that difficult if you really look at it and think of it as a mathematical graph, and you have the values here. But often in the classroom I see students being confused with that. So let's clarify that here, for example, we have a value of plus 20, and then here we have plus 40. Here we have negative 20, and then here we have negative 40, let's say. And so my goal now is to actually use this graph to bring down my values. And let's start with the first one at 43. That, let's say, would be somewhere here. And then the next one would be there. And here we would have one. And then here we have the 0. So now the question is, can we extrapolate our understanding? And can we now actually predict what the value would be at x equals to, let's say, 3 meters? So somewhere right here. Would we know what the value is at x equals to 2 meters, and so on and so forth? And when you look at this picture and you really think about it, you probably can do that because you have the 43.3 here. And remember what we did last time, we actually made a cut that encompassed all this portion here, and we then calculated the internal forces. And if you look at that formula, please understand that the lengths here, the 4, actually didn't play a big role for that particular part. This is very unique in this case, right? So it's particular to this case, so don't extrapolate that understanding. But what you can say is that, hey, if I would have cut the system here, or here, or here, or here, or here, or here, it would always come out to be 43.3 negative. And why negative, by the way? Because remember that the negative means that the member is in compression. So you push with 43 here from the left, and you balance it here on the right, because the horizontal component of the 50 with the angle of 30 leads to a component of 43.3. And so in other words, the beam is completely in equilibrium between point A and this force. And here everything has to remain zero because there's a roller here and the roller is pretty much pulled to the left, and because it doesn't resist the pull, it is free to move, it has a degree of freedom in that direction, there can be no force activated in here. So think about what force is. Force is really a resistance to deformation. And so this here really resists the deformation, whereas this one doesn't. It can actually move with it. So it's zero. And therefore, I can now extrapolate my understanding and really draw the values everywhere along the x-axis. So for example, if I wanted to know how much it is at 1 meter, I would probably say, hey, it's also minus 43.3. At 2 meters, the same, and so on and so forth. I can do that everywhere along the line. And again, when I move to the right here, I would actually say it's 0 here, 0 here, 0 here. But of course, we want to show this continuously and not at each individual point. So what we do is we actually draw a line. And in this case, you can see it's a constant or a horizontal line. And that needs to now jump back to 0. And that happens right here because of the force that is acting there in the horizontal direction. And then here it's all 0. And of course, I have to indicate that it's 0 here. In fact, let's talk about the 0 at x equals to 0. So at the very left point of the structure, there must be a force of 0 technically, and then the 43.3 comes in, and then it pushes it up. So in other words, my normal force diagram has to start at 0 and then go to the negative 43. And now it's almost a complete normal force diagram. I have to indicate the area that is really of relevance here. And the way I do that is by indicating, first of all, that it's in a negative region. And second of all, I have to shade the area. And I also, of course, have to indicate that it's 0 here. So I cannot just leave this blank. This would just mean that I didn't know if it was 0 or not. But this now is a complete normal force diagram, which has the identifier, it has the unit, it has the area that is in compression, it has the values, and it is complete therefore. So now last thing, like what you probably would do later in real life, instead of writing the values up here all the time, although this is very helpful for beginning engineers, but later on you probably would see it with 43.3 negative in that direction. And I invite you to really think about what this means. So this here is negative because this part is in compression, and that's important to understand. So if you really internalize that, you can easily draw these graphs later on because you will be able to see where a member is in compression, like here, or where it is in tension, and so on and so forth. But this will come through practice. This, of course, is our very first example. Let's now go ahead and draw the shear force diagram. And of course, I invite you to do that yourself. You know already that you need an identifier, and the identifier in this case is the V. So I put the V here, and this also happens to be in Newton. And this would be identical. We have an x-axis that goes to the right, and then a vertical axis that identifies the shear force in Newton, but you will never see this, so I'm going to spare this now. What I will do instead, I will bring in the values from my lecture 13. And the first value that I calculated at x equals to 3.99999 was plus 11.43, if I'm not mistaken. So the way I'm going to do that is I'm going to say that this here is plus 11.43. And this is just a help for me right now. That has nothing to do with the graph yet. I just want to bring over the values. I'm going to bring over the next value, which was plus 1.43. And then I had a value of still plus 1.43. And then I had a value of negative 23.57. So negative 23.57. Now let's think about how we graph this. Let's start with the values that we have, and that should be fairly easy. Remember that positive now is on the opposite to the reference fiber, so I'll just claim that I have a positive 11 point something right here, 11.43. Then I go down to 1.43 and I claim that's here. And therefore I have the same value here on this side. And now I go down to negative 23. And let's pretend that's right there. So far, so good. That is probably easy for all of us to do. Now think about what affects these values and the equations that you see in your previous lecture. And what you will find is that because we're dealing with concentrated forces here, this is only concentrated forces, you have no effect of the distance. So what I mean by that is, remember that we cut this system here like this, and that was the value that we received with 11.43 here in the first instance at 3.999. So that is because I cut the system here. If I would have cut the system at, let's say, 2 meters, the value would have come out to be exactly the same. So 11.43, because the equation would have looked exactly the same. So take a deep look at your equation in front of you from lecture 13 and notice that the length of this member did not contribute. And what I mean by that is that now I can go ahead and actually calculate or draw the values. I can draw it here, I can draw it here, I can draw it here. And you will see that once again it's a constant. Now take a look at the equation for the shear force that you prepared for this location here for 4.00001, and then compare it to the equation that you wrote down for 4.99999 at this location. And what you will find is that the length here, the 1 meter, also does not contribute or does not play a role in that particular equation. This will be different later, so be careful with that. But hopefully you see that you could have graphed the value here, 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 and so on and so forth. And now if you understand that, you may believe me that if I make a cut here and here and here and here and here and here, I would find the same value as I would find over there. And so I can graph that, of course, as well. So I can just move in this way. And as I mentioned before, our goal, of course, is not to draw every instant of the value, but rather to act like functions here. So I have a constant here, and then I have a constant right down here as well, and I have one here. And this, of course, is not a full graph yet. Why not? Because I need to do the same thing that I did for my normal graph here. Here I started at 0 and I also ended at 0. And so here I would also start at 0, and the first thing that brings it up is this 11.43, right? So we go up to 11.43 right there. And so the first thing that you can memorize for sure for each of these graphs is that you always start at 0. Okay, and then if I reach the next instance where I have a jump in the force, I have to, of course, go down, and I do the same thing here. And then, similar to my logic that I used right here, I have to end up at 0 here as well. So I cannot keep this open here because the value has to go back to 0. And if you don't believe that right now, you will definitely believe that if you have some practice with these problems. But now it's a closed diagram or a closed shear force diagram, which I complete now by my plus and my plus here and my negative. And I have to indicate this. And students always ask me, is this really necessary? This is just a waste of time to actually shade the area. And no, it's not a waste of time, because these graphs will become more complicated as time goes on. And then you have to clearly identify that you understand where something is positive and where something is negative. And then the way you would see it in the real world would be, you would have here plus 11.43, plus 1.43, and then minus 23.57. And that is now a complete shear force graph, which has an identifier, it has a unit, it has what's called significant values. So these are the significant values, and it has the shaded areas and the positive and negative clearly identified. Now, what is a significant value? A significant value is a value that represents the entire behavior. So from here to here, it's 11.43, then we have a jump. Then we have 1.43 is another significant value. And then we have another jump. Let's talk about the jumps real quick. In fact, you might have already seen this. So what is the jump really? So the jump here in this case is what? RAY. And why is it that jump? Because RAY is really what introduces the shear force. Remember what a shear force is? A shear force is a force that is perpendicular to the axis of the beam. In this case, it's in the y direction. So we can understand that every force that acts perpendicular to the beam, like the 10 and the vertical component here, have to have an influence on the shear force diagram. And you see it here, RAY. How big is this jump here? That jump is exactly the force of 10 newtons here on the top, right? So that jump is 10. So this is 10. This is just for education. Nobody would write this later on, right? But I want you to see that we have a jump of 10 here. And then what other jump do we have? We have a jump here that I'm going to copy over to the other side. So we have a jump that is right here. And that jump is actually equal to 50 times sine 30, right? Because that is the vertical component. And then we have a last jump here, which is equal to RBY. All right, so now we understand every element of the shear force diagram, and let me show you the very first shortcut to drawing these diagrams, which you should take with a word of caution because I don't want you to immediately use them. I first want you to really develop an understanding, but just because it's such a pretty picture here, I can show it to you already. So I started at 0, and it's important to note that the reference fiber is on the bottom and where my arrows point, right? So I have 11.43 here. So I'm jumping up and then I move to the right. Again, I can move to the right because my reference fiber is on the bottom because that's the positive x direction. So here's how I do this. Okay, jump 11.43. Nothing happens, nothing happens, nothing happens, nothing happens, nothing happens, nothing happens, nothing happens. Ooh, 10 happens. Okay, I jump down by 10. Nothing happens, nothing happens, nothing happens, nothing happens. Ooh, something happens. What is the jump here? The jump is 50 times sine 30. Nothing happens, nothing happens, nothing happens, nothing happens. Or I should show it here. Nothing happens, nothing happens, nothing happens. And then I bring back to 0 with 23.57. And boom, I have my entire shear force diagram created. Now, don't think that is always that easy. You can always use that logic, but it's not always that easy. What I want you to understand for now, before you see more complicated problems, is that we just follow the arrows and move to the right. And that works actually in all scenarios, but sometimes it becomes a little bit more difficult to implement. However, you have now created your very first shear force diagram. So therefore, it's time to move on to our moment. And let's think about the moment. And maybe you can go ahead and draw the moment diagram for yourself. Maybe you want to try that. Of course, you already know that you would put the identifier here and then the Newton meter as the unit right there. And now maybe find the values and graph them for you. You can click the pause button. I'm just going to continue. The first value that we found was what? 45.72 if I'm not mistaken. So we found here plus 45.72. We also found here plus 45.72. And then on the other side we found 47.15. So plus 47.15 and then plus 47.15. Of course, if I had a piece of paper in front of me here, this would be clearly separated from the shear force diagram, but just so you can see the structure itself, I'm going to have to do it like this, and now I can start drawing this. And please note that these are all positive, right? And that they are equal and equal here. So I'm going to graph those now. I'm going to go ahead and pretend that this here would be 45.72, and then the next one is a little bit higher. And now I have to think about how do I continue to draw this graph. And now it's very important that you go back to your equations in lecture 13 and look at the equation that you used to develop this first value. What was in your equation? Your equation included this cut, and you had 11.43 multiplied by 4 meters. So what would that really mean if you were to cut the system at 3 meters, 2 meters, 1 meter? So take a look at that equation. 11.43 times 4 was the value that you got here. If I cut at, let's say, 1 meter, my equation would say 11.43 times 1. At 2 meters, it would say 11.43 times 2. At 3 meters, it would say 11.43 times 3, and so on and so forth. And so what that means is I am not having an easy time anymore with a constant function. I now actually have a sloped function or a linear function, because the lever arm, which we used 4 to get this value, is actually linearly increasing from left to right. So the further I move away from the support, the larger the lever arm becomes in a linear fashion. What that also means is that at A, the lever arm is 0, and so I actually already know the next value. I know that this must be 0. And of course, you could have told that before, because we have here the hinge indicated, right? So this point here acts like a hinge. Sometimes teachers are not as nice as I am to give you actually the circle here, and they just assume that you know that the moment there's 0. But the reason I'm giving you the circle is to remind you that the moment there must be always equal to 0. And therefore, I also know that it must be 0 here on the right side, under B. And once again, we have only concentrated forces acting on the system, including the support reactions. And therefore, it's always force times lever arm. And the lever arm is always linearly increasing. This will be different in the future, but for now, for concentrated forces, we can, of course, draw functions that are linearly increasing. So I can connect these points, I can connect these points, and I can also connect these points. And I really invite you to really understand this through, for example, finding the value here in the middle. So go ahead and set up that equation by cutting the system either this way or this way and find the value here. And of course, you could mathematically already tell what that value is from this graph, but I want you to really be able to understand how these values are mathematically and physically derived. So physically is what we did in the last class, mathematically is what we're doing here right now, or what I'm trying to take you to. So let's complete our graph here. This is all positive, and I need to indicate my area, and I need to indicate that this here is plus 47.15, and this here is plus 45.72. The reason I'm doing this here is not to repeat myself, but because this is a significant value and this is a significant value in the context of the moment diagram. Why is it significant? Because the slope changes at that point and at this point as well. And of course here 0, we know that it's 0. So this would be full points on an exam. Now I want to direct your eye to something very specific here, and maybe you've seen it already, and of course in the classroom I could ask you. Right now I cannot. It's a very teachable moment, so I love those in the classroom. But please go ahead and ask yourself if you see some relationship between the shear force diagram and the moment diagram. Look very carefully and tell me, well, you can't, but think about what the relationship here is. I give you a few seconds and then I will, of course, tell you what it is. Yes, you are absolutely correct. There is a relationship, and the relationship is the shear force is the derivative of the moment. So what is the derivative really? The derivative is the slope of the function, right? So here I actually have a slope that goes from 0 to 45.72 over a length of 4 meters. I say that again. I have a slope that goes from 0 to 45.72 over a length of 4 meters. And that slope therefore is positive 11.43. take that in. The positive is important and the 11.43. The positive means that we actually have a positive slope here, right? It goes from positive x to positive y. That's the indication of the slope here. It goes diagonal upwards in this case. And so that's a positive slope. And for every meter I go to the right, I'm increasing by 11.43, to no surprise. That's actually reflected in your moment equation. Now let's take a look at the next easier part, which is this one here. And you can see that the slope here is minus 23.57. Minus means it goes down, diagonally downwards, if you will, from left to right. And that happens over 2 meters. So 47.15 divided by 2 with a negative slope is actually negative 23.57. And then you can convince yourself that the distance between this point here, 45.72 to 47.15, is actually 1 meter, and therefore the slope is 1.43. So we're looking at a slope of plus 1.43, plus because it goes up here. So one important thing that we just discovered is that the shear force is really the derivative of the moment over x, right? So what we have done without noticing it is actually differential math, because if you take a look at this function, it's really the derivative of that. And that tells us one very, very, very important thing about the moment function, besides the ones that we already talked about. But please memorize this one here, right? That the shear force passes through 0 where the moment is maximum, right? If you have done derivatives in the past, and you did if you are in this class, then you know that the function that goes through 0, that is the derivative, reveals where the parent function actually has a maximum. And so this is true here, right? So we don't have a maximum here because we didn't jump from 11.43 below 0. We only jumped to 1.4. But here we jumped through 0, and therefore we have our maximum value here. And that's always true. And so this is actually a very important aspect to remember. And therefore I want you to highlight this and really engrave it in your brain so that we understand this formula here. And we understand that the shear force is really the derivative of the moment. And if you pay very close attention, you can see something else here, which is not obvious. It's not like in your face obvious as it is down here for this one. But here you can think of this as the load case, and let's call the load case actually W. So I'm going to call the load case W. And what you can see is that also relates to the shear force. Here's a constant, here's a constant, and here's a constant. And what is the derivative of a constant? Is 0, 0, 0. So really what we're looking at here is dv dx. And the reason I have not included an equal sign yet is one very important aspect. And that is something that is probably the reason why you did not see that this really is the derivative of this load case, or sorry, of the shear force diagram. It's because this is actually the negative. So the arrows here are pointing downwards, and therefore the W would have to be negative here. So this is negative, and now it's equal. So the inverse of the derivative of the shear force is really the load case. So if you want to put the minus on the other side, that's what that would mean. But this is very important for us to understand, and we clearly understand that there's a mathematical relationship between the load case and the shear force diagram, and there's a relationship between the shear force diagram and the moment diagram. You could, of course, do that the other way around, and you could state that the moment function is really the integration of the shear force function. The reason I haven't done that, some teachers would write that out as saying that, hey, the moment is the integrated shear force, but be careful, because what happens if you integrate, when you integrate a function, you usually end up with integration constants. And we do not yet know enough about that here in this class, how that relates. That will be part of the upcoming problems. but please understand that conceptually it can help you to think that this is the integration of the shear force. So the moment is the integration of the shear force, but you have to treat that with caution because sometimes you have integration constants. One last word about the moment here, and another thing that we can use to really validate our results. Notice that everything here is a positive moment. And that makes perfect sense if you think 1 or 2 lectures back when we actually defined how our internal forces are really properly arranged and properly defined. We said that a smiling beam that would like bend downwards has a positive moment on it. That's defined by the moment that turns clockwise on the left cut and counterclockwise on the right cut. Take a look at your note card. So we said that those moments always create a positive bending. And you can see this here in this diagram. So you can see that this beam must be smiling all the way from here to here, because from 0 all the way over to the 7 meters, 7 meters. So all the way over to the 7 meters, the beam is smiling. And of course, an engineer would never say that it's actually smiling. An engineer would say it's bending downwards. And therefore, you have tension on the bottom and compression on the top. I say that again. So if the beam bends downwards or deflects downward, then you have tension in the reference fiber or on the bottom and compression on the top. And that is what we defined as positive moments. And therefore, you can take this here as an indicator that we answered this correctly, because you can physically say that this is pushing down, this cannot move, this cannot move, and therefore you must have a smiling beam, and the positive here indicates that it is a smiling beam. So as you can see, there are many valuable lessons that we can take away from only a simple problem like this one, as long as we spend dedicated time on really analyzing how they relate to each other, for example, and how engineers display them. So let me recap what we have seen here and what you need to be able to do in the future. You need to be able to draw the diagrams, and to do that you need to include the identifier, you need to always include the unit, you need to include the significant values every time something changes somewhere, and you need to indicate if it's the negative region or the positive region, because the negative and the positive region has specific meaning. So for example, positive bending means the beam is bending downwards. Negative normal force means that everything is compression, and so on and so forth. But we will talk about this more in future problems. For now, I believe we have a good introduction and a good overview of what we need to do. And now it's time to practice it through another problem. And then I think you're ready for your homework. But please don't be fooled. My experience in the classroom is that students tend to get confused if a single aspect of the problem changes. So for example, if there's another force that pushes up, or there's another distributed force somewhere, then all of a sudden the problem appears very different. And that is totally normal. At least that's how I felt when I first learned this material. I looked at it and everything looked different to me. But in reality, it's always the same. And you can always apply the rules that we applied here today. So please understand that that is the reason why we have so much homework in this class, because if we don't expose you to different scenarios, you think that it's all solvable with one method, and you'll be surprised in the real world how different things would be then. So practice makes perfect, and you have the chance here through your homework to really be exposed to many different examples that really help you to be very, very, very prepared. So what I guess I'm saying is you're welcome for all the homework. I know we sometimes disagree on the amount of work, at least students and teachers do so, but hopefully you will see at some point that it makes sense and that none of these problems is actually a waste of time. In fact, they prepare you for very specific scenarios until we are ready to really understand these problems in depth. With that said, I believe we have mostly everything in place to tackle the homework, but practice makes perfect. So let's go through one more example problem before we apply our knowledge in the upcoming homework. Let's move on to the next page. All right, so we have our first beautiful internal force diagram problem here in front of us. Let's take a closer look and understand what we are supposed to do. So first of all, we have to calculate the internal forces at location B and C. That is indicated by these dots here. Those are not hinges or anything. This is just identifying the location. And then when we're done with that, we have to draw the diagrams for the normal force, the shear force, and the bending moment. But please keep in mind that this lecture is also designed around a classroom lecture, so that for time reasons I only make students calculate the internal forces here and here. What probably would be good for you would be to calculate the internal forces to the left of the 9 kilonewton meter and also to the right of the 9 kilonewton meter. Just set up the cut and the equations for that, and that will help you to draw the diagram. Due to time limitations in the classroom, even though it's a virtual classroom, I will take a shortcut when it comes to this one, and I will show you how that is done. But you should practice that for sure. Some of you will be faster than others, but practice definitely makes perfect. And at the end, we all have to be fast to be prepared for the upcoming exam. All right, but let's get started and calculate the support reactions at A and B. But before we do that, take a look at the system and understand that we have 6 kilonewton pushing down here, and then we have 9 kilonewton meter rotating the system counterclockwise. What does that mean? That means that this vertical force here causes an upwards reaction here and an upwards reaction there, but on the contrary, the 9 kilonewton meter rotates this up and this down. And therefore, we need to have a reaction that at D pulls down and at A pushes against that. So obviously, the support reaction is a combination of this plus this, and we will now go ahead and calculate that. And to do that, I will first draw my free body diagram. And as always, it's a free body diagram of a rigid body. That means that I have to also include my dashed fiber. And I have, as always, my 3 support reactions. I have a horizontal reaction at A because that's where the pin is located. I have a vertical reaction here, and I have a vertical reaction at D. And I'm going to call this RDY, RAY, and RAX. And we can already say that this is equal to 0, so this is done. But I have to now bring down my forces here. And this is the 6 kilonewton. And I have to include my 9 kilonewton meter. And so that now is my entire system. The whole beam is 9 meters long, if I'm not mistaken. So yeah, 3 plus 4 plus 2 is 9. And so I can now quickly actually calculate the support reaction. If this puzzles you, please go back to the calculation for support reactions. I think we started that in lecture 10 or so, but I can just say that, for example, my RAY, and I need my numbers here from the top, so my RAY is nothing else than 6 kilonewton multiplied by 4 plus 2, if you will, right? 4 plus 2 divided by 9, that's the entire length. And then plus, because it's reacting to it, plus 9 divided by 9, so that's 9 kilonewton meters divided by 9 meters, right? And again, if that puzzles you, please go back to support reaction calculation. Of course, the other one has to be complementary, so we're looking at 6 multiplied by 3 divided by 9 minus, because I have to pull down here to keep the rotation from not rotating counterclockwise. So minus 9 divided by 9. And now I can solve this, and I can find that my RAY is really equal to 5 kilonewton, and my RBY is really equal to 1 kilonewton. And please keep in mind that the 1 kilonewton is really going up, and the 5 kilonewton is also going up. So I don't even need to worry about flipping any signs or anything, but that is the results you should find. And now you can go ahead and actually find your internal forces through cuts. I will do that on the next page. If this confuses you, we have some room here for calculating support reactions. That's what this space is for. Go ahead and just set up the equation. Rotate about this point, rotate about that point, and you will find your equations. But I will move on now using the 5 kilonewton and the 1 kilonewton, and I will see you on the next page. On this page, I will now go ahead and draw the internal force diagrams for any location I need to find the values. So look at the headline here, and please understand that you have to calculate your internal forces via as many individual cuts as necessary. So this is different from student to student, and initially I always recommend to do like as many cuts as you possibly can. So do many cuts, but at the end you want to do it just as it's necessary for you. Of course, in this problem I'm asked to find the internal forces at location B and C, so I will now draw the free body diagram first for those. So I will draw the free body diagram for cut A to B, which, if we remember that correctly, that was just the left side of the system. So I have my free body diagram here, which how that works we really showed you in the previous lecture, but I cut it here at at B, and I had support reactions which were 5 kilonewton pushing up here, 5 kilonewton, and I had a 0 here, so I don't even worry about that. But then there was no other force on the system. Remember that? There was no force except that one. And what I do next is I will bring in my internal forces that therefore become external forces. So for example, I use my little study card, which tells me that the moment goes in this direction, the shear force in that direction, and the normal force goes in that direction. So I now indicate them, and I call them M at B, V at B, and N at B. And you can already tell that due to the sum of the forces in the x direction being equal to 0, N at B is really equal to 0. I don't have to explain that. But for the sum of the forces in the y direction being equal to 0, I use upwards positive. And 0 is equal to minus positive VB plus 5 kilonewton. And so therefore my VB is really equal to 5, and that is positive 5 kilonewton. And that is a result that we will use later on. So I'm not going to double underline it here because I will just use it in my diagrams. Now for the moment, what do I do? To calculate the moment, I take the sum of the moments about point B equal to 0, counterclockwise positive in this case, and 0 is equal to plus positive MB minus 5 kilonewton with a lever arm of 3 meters. So the distance is 3 meters to point B, and negative is the rotation in the clockwise direction. So therefore I know now that my M at B is equal to plus 15 kilonewton meter. Once again a result, but I will use that result in a diagram later on. But sometimes it helps me actually to find the values faster as I solve them. So I will actually at least single underline each of these values so that when I look for them later on, I will know where to find them. Okay, now we are ready to actually make the next cut, and the next cut was at C. And to do that, all I have to do is extend my free body diagram a little bit. So I'm going to do the free body diagram for A through C, if you will. And the way that looks like is very similar, just a tiny bit longer. So you could think of this as being 3.00001 long. And of course I have my upwards force still here, and that is 5 kilonewton still. But I also have my downwards force right here, which that was given with 6 kilonewton. And now I have to cut right at that location C and bring in my internal forces, my moment, my shear, and my normal force. So V at C, N at C, and M at C. And I can now set up my equations. Before I move on, just notice the only difference between this and this is really that we made this a tiny bit longer here and therefore now include the 6 kilonewton. All right, so now I can go ahead and calculate my internal forces at that location. So for example, the sum of the forces in the x direction is equal to 0 really tells me that NC is equal to 0. That is a result that I will use later on. I also have to find the sum of the forces in the y direction being equal to 0. And I pretty much say that 0 is equal to minus positive Vc plus 5 kilonewton, that's a support reaction, minus 6 kilonewton. And now I know that my V at C is really equal to minus 1 kilonewton. And that is something I will use later on as well. And I'm ready to move on to my moment. So the moment at C is really determined through the sum of the moments about point C being equal to 0, counterclockwise positive. And 0 is equal to, I always start with my unknown, plus positive defined MC minus 5 kilonewton multiplied by 3 meters. The distance is still 3 meters there. And then I have to include the 6, but the 6 really has 0 lever arm, so you would say something like plus minus 6 kilonewton multiplied by 0 meters. That's really how that would work, but the distance again is so short that it has no effect. It would actually be positive because it would rotate counterclockwise, but let's forget about that. And let's understand that the moment at C remains plus 1.5 kilonewton meter. And that is something that I need to find later on in my diagram, so therefore I'm highlighting it as well. All right, technically we are done now according to the problem statement before we draw the internal force diagrams, but for educational purpose I want to move on from here to the concentrated moment that would be acting somewhere here, and I'm going to pull in the reference here real quick to help you understand what I'm talking about. So let's actually bring in this picture and let's now find the internal forces to the right of this moment. You can yourself determine them to the left of this moment, but for speed reasons here, I'm just going to look at that location. And to do that, I'm drawing my free body diagram of that portion. And also this will give us an opportunity to use the left cut actually. So now I'm cutting right here. And my support reaction now actually has a value of 1 kilonewton here. And I will bring in my card, the other side of the card now that I flipped into half, and you will find that the moment goes in this direction, shear force in this direction, and the normal force in that direction. And this now would be, of course, at location 7 meters to the right. So really we can call this here M at 7 to the right, V at 7 to the right, and N at 7 to the right. So let's go ahead and calculate the values. By the way, this is the free body diagram for, let's call it C, well, 7 to 9 meters, if you will. All right. And please note that I always, when I draw a free body diagram, it's always including the entire either right side or the entire left side. So I don't want to have a free body diagram that is somewhere dissected from the middle that doesn't include everything to the right or doesn't include everything to the left. You can technically do that if you really know how you do it and what you do, but for this beginning purpose, it's not a good idea to do that. So for now, always include either the entire right part of the structure or always the entire left part of the structure. So before for B and C we used the left side, now I'm using the right side, and therefore I have a different cut. And now I can use the easy numbers here now. For example, the sum of the forces in x is equal to 0, and that will tell me that n at 7 to the right is really equal to 0. That is a result. And the sum of the forces in y is equal to 0. That will help me to understand that 0 is equal to, and now I'm using plus positive v7r. So that's v to the right and 2 positives because it's acting positive and it's pointing down upwards. And then plus 1 kilonewton. And so I know now that my v at 7 to the right of it is really equal to minus 1 kilonewton. And you may have already predicted that, but again, it's education here. So last but not least, I do the sum of the moments about 0.7 to the right, if you will. It's equal to 0, counterclockwise positive. And 0 is equal to, I start with my unknown, positive m7r. But that turns clockwise, therefore it's a negative rotation. And then I have to pay attention here. So this now, the 1 turns about this point counterclockwise with a lever arm of 2. So I'm using 1 kilonewton multiplied by 2 meters. And it's rotating counterclockwise. Therefore, this entire thing here is positive. And therefore, I now find that my m at 7 meters to the right is really equal to 1 times 2, right? So plus 2 kilonewton meters. And it's important that you get that right, because if you somehow messed up the sign here or the sign here or the sign here, you would not find it to be positive. And that is, of course, important in an engineering context for these problems. And again, I invite you to now draw this diagram and actually include the 9 kilonewton meters here to the left of it, and then run these equations and find the answers. But I am ready now to move on to the next page and draw all the diagrams. Let's take a final look at here what we did. So I did decide to make my cut from A to B, from A to C. That was per definition. I found my normal force, my shear force, my moment, my normal force, my shear force, my moment. And then I also decided, because I didn't know what's going on here at this location, to make another cut. And maybe if I were a beginning engineer or like somebody who hasn't had a lot of experience with these internal force diagrams, I would probably make another cut at, let's say, 8 meters, maybe somewhere at 5 meters, maybe somewhere at 1 meter, just so that I can really practice and learn how these values come about. But for me, this is enough now to really draw the diagrams, and I will do that on the next page, and I'm looking forward for you to join me there. Alright, so here we can see the very nice solution page where we have the luxury that the teacher was so nice to give us the structure itself lined up with the 3 diagram bases, if you will. And I guess you're welcome. But now we have to include the values that we calculated on the previous page. It's really helpful if you take a look at the previous page, or that you have it side by side with you right now. I, of course, here have a computer screen, so I cannot have that next to me because I want to focus on this one. But believe me, I have the values right next to me as well. You just cannot see them right now. But let's go ahead and first bring down our lines here. That always helps me to line up my diagrams better. And then also the next easiest thing to do is probably to draw the indicators for the individual lines, for the individual diagrams, I should say. So of course I start with my normal force. So let's put the normal force right here. And in this case, we're dealing with kilonewton. So I have to put that unit here as well. And here it's super simple, but I still have to show it for each of my individual parts. Everything here was 0. I didn't have to do any calculations. So I indicate that this is 0, this region is 0, and this region is 0. I could also call this a domain, by the way. In fact, let's do that. Let's call this here domain 1, domain 2, and domain 3. That will become more important in one of our next lectures. But now I want to move on to the shear force diagram. And for my shear force diagram, the first value that I calculated at B was equal to positive 5, if I remember this correct. So let's say this here was equal to positive 5. And then at C, I had a value of minus 1, if I'm not mistaken. So that looks like this. And for the other location where I also calculated, remember I also calculated it here, right? So somewhere at this location to the right of that line. And I found that that was also minus 1. Now, can I extrapolate my understanding from previous problems and from what I've learned as I set up the equations? Yes, I can. So what influences the shear force distribution from here to here is really only the support reaction. And remember, that was actually 5. So really how I should draw my diagram would be up with 5, because that's my RAY. So this is RAY. And then after I have RAY, I can move, because nothing happens, nothing happens, nothing happens, nothing happens, nothing happens. Ooh, something happens now. How much does happen? It happens with 6 down, right? So 6 down. And then again, nothing happens, nothing happens, nothing happens, nothing happens. And oh, something happens now. I have to go back up to 0. And so this is my negative region now, and this is my positive region. And notice one important thing that I will explain to you after I completed my diagram here. Notice an important thing. Number one, I forgot to indicate that it's the shear force and that it's also in kilonewton. But really what I want to put your attention to is that there's a moment here, a concentrated moment, which you see that right, there's no influence on the shear force diagram. So the concentrated moment happens to have no influence, and you can see that in your equations on the previous page. I invite you to go there and study them, but you believe me here probably that it has no impact. So I have for full points also to include that this here is equal to 5 plus 5, and this here is equal to minus 1. And now I'm already ready to move on to my moment diagram. So first let me indicate it before I forget that again. This is in kilonewton meters. And now I can find my values that I calculated first for B. What did I calculate? I calculated that to be plus 15. So let's pretend that's right there. And then at C, I also calculated it to be plus 15. So of course, in reality, it is at the line. So I'm going to erase this real quick and actually put the X directly on the line. So I pretend that this here is plus 15. And I also calculated the value right here with positive 2, so that I can actually draw a little cross right down there. And now it's very tempting to say, if it's plus 2 here, then maybe it's plus 2 on this side as well, because that was the case for this location. But notice that here at B and C, we're actually dealing with a concentrated force, whereas here we are dealing with a concentrated moment. And so the concentrated moment will have an impact on your equation if you extend the cut that we did actually for the right side of the system. In fact, you will find that then you have the 9 rotating counterclockwise and therefore going against the moment that comes from your internal force definition that is located on your little study card. So therefore, you will actually find that this bumps up the value by 9. So really what I will end up with is with another cross right up here. And remember that this value here was plus 2. And then we have plus 9. So this is plus 11. And that makes perfect sense. And you will see this when I draw the diagram. And I will repeat that then. But because you don't have it drawn when you have to go through this thinking process, let me just show it to you. So this makes perfect sense because the slope is minus 1, right? And to get from here to plus 2 is impossible with a slope of -1 over a length of 4. Instead, you have to go from 15, remember that this here was plus 15, right? Plus 15 can only go to 11 over a length of 4 meters with a slope of -1. So, and notice that it's also a negative slope here. And last but not least, the thing that you always know for your moment diagrams is that here is a hinge effectively, and this acts like a hinge, so you can think of this as a hinge, and therefore the moments must be 0 there. And final observation here for the moment diagram is that if I were to make this cut here, for example, that I made for B, that the only thing that had a moment or that created a moment about point B was the support reaction. And that support reaction is dependent on the distance, and therefore if I increase my distance linearly, the moment will increase linearly. And so that's reflected here in the 5, right? So the 5 is the slope over 3 meters. And the last thing that I have to do therefore is actually connect my points properly. Of course, I've seen students always being able to connect them, but the question is, can they connect them properly? And so I have the first one, and then the next easier one is probably the one down here. So that one. And then I have a last sloped line. And important here to understand, and that's the educational lesson of this problem, is that I also have to make this connection. And so you understand that this jump here is really +9. +9, be careful, you cannot always say because it's clockwise or counterclockwise, therefore it's plus. It really depends on the cut and the system. So please use that with caution, but also make sure that you indicate what your area is or where your positive area is, and indicate your significant values, right? So these are the significant values here, because those are the values where something changes. And please note one thing. Yes, we said before that V is equal to dm dx. That is something that you memorize from now on for good, because it's very important. And it is true, but remember the problem that you have if you do it the other way around. So what do you do from the shear force to the moment? You actually integrate in this direction, right? So in fact, I kind of, in my head, without telling you, although you probably noticed it, I integrated when I drew this line, right? I said that this line must have a slope of -1, or this line has a slope of +5. And so students are very tempted to take a look at this diagram and then just in their head integrate to draw these. But you would see this would not work out if you would not consider this jump here, the 9 kilonewton meters, right? So you can think of this 9 kilonewton meters actually as an initial or boundary condition here if you do the integration. So please be careful when you just integrate from the shear force to the moment diagram. You find this often recommended to you in the literature, and this is of course correct, but you have to understand the entire physical meaning of the system. And here is just one example of that, where you see a concentrated moment, and that has an impact on your diagram that you would not find by simply integrating these functions here, the +5 and the -1, where the function is a constant. I understand that, of course. But this now completes our entire diagram, and we of course understand the general relationship here. For example, the maximum moment is located where the shear force passes through 0. We have the connection of the slope to the shear force magnitude here, and therefore we applied our knowledge one more time. And I think that concludes our lecture, and we can now move on to the final page and summarize our findings. All right, time to wrap up our lecture and think about what our takeaways are and the parts that are still a little bit muddy to us. It's very important that you clarify that for yourself so that you can now honestly answer the questions on the bottom, which I will move on to now. So let's look at those And let's really understand these, because this will be your bread and butter for the rest of this class and for exams and so on. So it's so important that we really, really honestly answer these questions correctly, or these checkpoints correctly. So the first thing I need to understand is that I can really make a virtual cut anywhere along the structure to find the forces at that location where I cut. So it is important that we understand that it's really any location, and the reason that I'm doing that is because I want to find the values for the internal forces at that particular location. That is technically a conclusion that comes from the last lecture, but it's so important before we discuss what we discussed here today about the diagrams. Because without that, we wouldn't even be able to start our diagram drawings. But that takes us directly into the next checkpoint here, for which we understand that the internal forces really are present at any location, right? Anywhere along the longitudinal axis of the structural element, if you will. That is important to understand, so that you really do not get confused between why did we calculate at a particular location before and why are we now drawing diagrams. We only did that for practice. So the previous lectures were really for practice. Really, we want to know how the internal forces act at any location along the member axis. And therefore, we are able to graph these internal forces now. And why do we do that? Because we want to use the graphing methods to represent the numerical values that exist anywhere and everywhere along the longitudinal axis. So please understand that we're really doing this so that we, in one concise graph, have everything in front of us, so that we have easy access to all the values that we need. And so what's really important for you is that you can actually use these graphical methods to completely display all the internal forces in any structure. In this case, only for structures that carry concentrated loads. That's what we focused on in this class. In one of our future classes, we will of course expand that to distributed forces and other structural systems. But for now, you can, for easy structures, understand that, and you know how to apply these methods for concentrated loads. All right, so therefore we are now familiar with all the aspects that must be displayed, and let me explain what all the aspects means in this context when we want to display a professional internal force diagram. And what I mean by that is the identifier for one, so normal force, shear force, moment. Then you also need to include the unit in square brackets. You need to include the significant values, right? We talked about that. And you have to identify if an area is in compression or in tension, so plus or minus. And you have to shade the area that is relevant. And all these aspects that we talked about in today's lecture. So you need to be familiar with that, because if you violate any one of those, if you forget any of these, you would not properly communicate in an engineering sense what your values are or what they relate to, and therefore you would have to lose some points on an exam, for example. And in the real world, worst case scenario, somebody doesn't understand what you're talking about. So it's important that you actually include those. All right, and then last but not least, it's very important that we understand that we can mathematically relate the internal bending moment to the shear force. And this can go to much higher levels than what we talked about today. And we will actually talk more about this in the future in this class, but this goes way beyond the purpose of this class. Engineers deal with this a lot later on for different engineering designs. Please remember, though, for now, that we introduced the concept that the shear force is really dm dx. So it's the derivative of the moment. Likewise, we also learned that the load case, which we call W, is equal to the negative of dv dx. We actually had the negative on the other side, but you find it in different textbooks one way or the other, either minus here or the minus here. It means the same thing. However, I hope we truly understand this after this lecture. At least I could visually convince you of that, and you can convince you further through the following homework. But this definitely summarizes our lecture, and we are now happy to study the homework and can take a look at the upcoming problems on the next page. Okay, so here we are at your favorite page, the homework page, and let's take a look at our 6 problems that now relate to internal force diagrams for concentrated forces. You can see that each of these problems have only concentrated forces. And the first one here is a simply supported beam with just 2 forces at specific distances. So this should be a walk in the park after we showed you the first example in this lecture. It's pretty much analogous to that, and I'm sure you are able to solve this, so I don't need to tell you much more here. Let me take you to the next problem. Here you have a similar scenario, but now you also deal with horizontal components. And please pay close attention to drawing the normal force diagram for this particular problem. That's the learning experience we're trying to provide here. But that is all we need to discuss for this problem. Let's go to problem C. Now it will become a little bit interesting. We touched upon the moment here, but we didn't fully explain that in the lecture on purpose so that you can expose yourself to this and really challenge yourself to find the shear force and the moment diagram. Let me tell you right away that the normal diagram for this is 0. And you might think, if the normal is 0, then the shear force is 0 as well. But that is not true, because you will actually end up with support reactions in the vertical direction due to the imbalance of these moments. If you are in the category where M2 is equal to M1, then you have a very special scenario. But you would have to explain why that is not solvable, or rather said, why it's 0 in that case. But I think I already gave that away. But other than that, there's nothing I can help you here with that problem, besides that you have to use it to apply your own individual numbers. Let's move on to the next one. And let's take a look at this cantilever beam here. So here we have a cantilever beam, which of course we didn't discuss today, but it has been discussed in other lectures, at least how we find support reactions. You know how to do that. And we discussed today how to find internal forces. Keep in mind that for internal forces, you can always release either the left side or the right side. And maybe, therefore, this is a very nice, easy, quick problem for you if you already understand how that all works. Because maybe you get away without even calculating support reactions. Or maybe you can use the support reactions to validate your results. But this is a learning experience we want you to go through. So I wish you good luck with that problem. And I move on to the next one, where now we have another cantilever that's supported on the right side in this case. So it feels maybe more natural to release the left side. For some reason, students always start cutting the left side, but I have to convince them in the classroom that it is the same. If you cut the left side or the right side, you will always find the same type of force at that particular location. But you have to draw the internal force diagrams anywhere, so you have to find it everywhere along the member. And I'm pretty sure with all the practice you get from the previous problems, that will be a walk in the park for you. Just note that here now we have a moment. And yes, we want you to really work your way through those. And we are not trying to spoon feed every information to you here, although some people might argue that I do that too much in my lectures. But you have all the tools, I think, from the lecture that you can use to solve this. But sometimes students tell me that it's too difficult. And my response to that is, we are engineers. We want to solve difficult problems, not easy problems, right? So if we would give you problems that you already know how to solve, what would be the point? So the goal obviously is to learn something, and we do that through these problems. Here I have a last cantilever for you, where you now also have to include the normal force diagram so that you can get through that learning experience as well. But that concludes the homework assignment for this lecture, or from this lecture, and we are now ready to solve these problems for concentrated forces. It is good if you complete this before you move on to the next level or the next lecture, because in our next lecture we will actually extend our knowledge and put distributed forces on the systems, and we will see what impact that will have on the internal force diagrams. But for now, you have everything you need to solve these 6 problems, and hopefully other ones as well that might cross your way in exams or quizzes. I wish you good luck studying the material. I see you in the next lecture. Until then, stay safe.